Welcome to this presentation on the lines and planes tools in Maple's Student Multivariate Calculus package. By way of introduction, let me make these remarks. At the beginning of the typical calculus of several variables course, there's typically a unit on vectors, lines, and planes, and I think it's there as an introduction to thinking and visualizing in 3 dimensions. The Student Multivariate Calculus package in Maple has some functionalities for working with lines and planes. There's a set of 16 commands that you could use, or you can do syntax-free computing through the context panel. So I'm going to give an overview of these tools, and I'm going to illustrate how they are used with a set of examples. And the examples come from the standard course or textbook in multivariate calculus. We'll begin by looking at the line and plane constructors. Because you're dealing with lines and planes, you have a way of telling Maple this thing is a line or this thing is a plane. Alright, so there's a line command that is a plane command, and I'll show you how you can do that through the context panel. Representation of these various objects. Points, typically a list in Maple. Throughout most of Maple, a list, square brackets, used to represent a point. Vector, you could use the matrix palette. The simplest way to type a vector in is to use these angle brackets, which are really just inequality symbols. You have a line object, so when you define a line, you get a line object that contains the information about the line, and similarly you get a plane object if you construct a plane. Now, how would you define a line? You could do it with an algebraic equation in the plane, or an expression, algebraic expression, which if set equal to 0 would be the equation of a line in the plane. In the plane or in 3 space, 2 points would determine a line. In 2 dimensions or 3 dimensions, a point and a direction, v being a direction vector, would define a line. Parametrically, 2 dimensions, 3 dimensions, you could have a list of linear expressions, and linear in the parameter. You could have a list of equations of the form coordinate name equals expression, linear in the parameter. So this would be, for example, x equals 1 plus 2t, y equals 2 plus 5t. Throw in a z coordinate, z equals 7 plus 8t. You could also define these parametric expressions in a vector. So you have a vector of expressions, each one defining the component of the appropriate equation. In 3 dimensions, 2 planes intersect in a line. So if you have 2 things that construct a plane, they would define the line of intersection of those planes. Point in a plane. You get the line through that point whose direction is the normal to the plane. So the line is orthogonal to the plane. In 2 or 3 dimensions, if you just have a line object defined according to the tenets of this package, that would allow you to redefine or change options on a particular line. Okay, for the plane, how would you define a plane? You have a linear equation, then the terms could be rearranged, or you just have a linear expression which, if set equal to 0, would define the plane. 3 points define a plane. A point and a direction. In this case, the direction is taken to be the normal. 2 points and a vector. Well, these 2 points would lie in the plane. This direction would be in the plane. These 2 points, by subtraction, you'd get a vector in the plane. You would have 2 vectors in the plane. Take their cross product, you get a normal, you define the plane. two vectors and a point. The plane contains these two directions and passes through this point, or contains this point A. Two vectors in the plane, you take the cross product, it gives you a normal. You have a normal and a point, you've defined a plane. Line and a point not on the line. This would define a plane that contains the point A and the line itself. Two lines. The lines are skewed, that is, they don't intersect and are not parallel. You get the plane that contains the first line and is parallel to the second line. And we'll do an example of this shortly. Point and a plane. So you get a plane that contains the point and is parallel to the given plane. Or you have a plane object and you redefine it and give it different properties. Now, I've shaded some of these items. The shading means that the order in which the building blocks are given doesn't matter. So what are the commands for interacting with line and plane objects? Here is the list of the Maple 16 commands. Get dimension. Well, you determine if you are in 2 or 3 dimensions, if it's a line in 2 or 3 dimensions, and so forth. Get direction. This would return a direction vector for a line. Get intersection. Well, intersecting two lines, two planes, line in a plane, what is the intersection? Get a normal. So what is the normal on a plane? This will draw a graph. Get plot. And this is the one functionality that is not available directly in the context panel. Get point. So if you have a line or a plane and you want an arbitrary point on the line or a plane, this will give you one. Get representation. So after you've constructed a line or a plane and you want to see an equation or a representation, algebraic representation, you say get representation. We'll see examples that illustrate what kind of representations you could get and how you get those. Intersect. So this is a query. Do these two lines intersect? Do these two planes intersect? Contains. Does this object contain that object? So does this line contain that point? Does this plane contain that line? Does this plane contain that point? Distance between two lines. Distance between two planes. Distance between a point and a line, a point and a plane. Are these two items equal? Are these two lines parallel? Are these two planes parallel? Are these two lines skewed? Are these two lines or planes orthogonal? What is the angle between two lines? What is the angle between two planes? And then projection. So you project a line onto a plane, vector onto a plane, and so forth. For equations, what is the form of the representation? You can say the form is to be the form of, take the form of an equation, you get an equation. If you put an S on that, allowing for multiplicity, you would get the equation in set brackets. If you say vectors, you get a vector representation. T is a parameter, you can change that, times the direction vector plus the fixed point. Parametric, you get parametric equations. Symmetric, you get the symmetric form, the equation of the line. If you say combined vector, then this vector representation is combined to give you these linear expressions in a vector. So that's 2D. In 3D, everything's parallel except right up here. There is no equivalent to the equation of a line algebraically as one equation in 3D. For a plane, it's much simpler. If you say equation, you get the equation of the plane. If you put an S on there, it's the equation of the plane, but it's in set brackets. So what are the things to keep in mind when you're working with lines and planes through the context panel? Basically, it's this. The constructions and the interactions can be done through the context panel. Sometimes the context panel will recognize the object that it's supposed to act on. Sometimes you have to do an evaluate and display in line in order to pass from the name of an object to the actual object itself. And you'll see this happening as we work through our examples. So let's see how many of these examples we can get through in the remaining time that we have. An equation for the line through a point and has this as its direction. Relatively simple example. Let's see how that would go. So here is the syntax-free version. Load the student package, a Student Multivariate Calculus package. You go here to Tools, Load Package. You go down here to Student Multivariate Calculus. So again, we're talking syntax-free. I think I'll reactivate that. And you see I've typed in some stuff ahead of time so that we're not spending time watching me type. Point and a direction. Point is a list. Direction is a vector, so you use these angle brackets. Right-click on that pair, or in fact, if you open the context panel by going over to this context panel side here, Student Multivariate Calculus, lines and planes, we are defining a line. You select line. And this would be the result. That symbol, which Maple displays on the screen, stands for the line object that has been created. I believe it's actually a module. I think of a module as a basket. In this basket are all the properties and all the information about the line. So then you go back to the basket, you rummage in there, and you pull out stuff that you want. So I think I'm going to re-execute this line so that you can see this next step. Line, multivariate calculus, lines and planes. Now you can query for properties of this line, and I queried for representation. So a panel came up, and this is the dialog that I'm putting in front of you. The variables of the coordinate system, defaults are x, y, z. I say okay because that's good enough for me. Once you say okay, this dialog comes up, which allows you to either change the parameter from the default t or to some other one, and then you can pick the form. So this is a drop down. You have the different forms. Combined vector is this one, and momentarily you'll see what happens if you make these other choices. And this is what it would look like if we use the set of commands. So the first thing I would point out is if you're working with commands and you're eschewing the syntax-free approach, then you have to type with Student Multivariate Calculus. You have to start to know some stuff here now. Colon equal is the assignment operator. This is the line command. It's applied to the point and the vector, and I have assigned this line object to this name so that I can reference the line object. If I want equation, I would use get representation. I apply it to L1. Form equals combined vectors. It's so much easier to grab this from a drop-down list and to have to look up the syntax. This is what we had above. If we say form equals parametric, you get parametric equations. If you say form equals symmetric, you get the symmetric form. And if you say form equal vectors, then you get the vectors not added together, but the parameter times the direction plus the fixed point. And finally, the traditional approach is a vector approach, and if you wanted to follow the traditional vector approach, this is how you would do it in Maple. Now, the vector P is the position vector to the fixed point. The direction vector is a vector. R is the position vector to the generic point x, y, z. Put an equal sign here. Use the context menu to assign name. That assigns this object to that name. So I did that. Then the vector form of the line, I've put the R equals, so that you get x, y, z on the left, equals point plus t times a vector, and Maple will automatically add p plus tv, and you get the essentially the parametric form, because it's x equals this, y equals that, equals that. So you can imitate the traditional pencil and paper approach in Maple. For a second example, let's get the equation of a line through 2 points. Again, syntax-free solution. Load the package, 2 points, so you have 2 lists. Make line, we saw that in the previous example, example 1. Get representation, I have again picked combined vectors. So to pop up here for the coordinates, to pop up here for the parameter and the form. This would be the essentially the parametric form, because x equals this, y equals that, z equals that. But it's not given as the set of equations, it's given in this vector form. To solve this problem via the set of commands, it's very, very similar to our first example. 2 points, apply the line command to it. Assign the name. You've already here installed the package, used with to install the package. Get representation, apply it to the name L1. Form, combined vector. It's the one we picked. If you say form equals parametric, you get parametric equations. Form equals symmetric, you get the symmetric form of the equations of the line. And form equal vectors, you get the vectors not added together. The traditional approach is through vectors. You would assign each of the 2 fixed points as position vectors. So you have these angle brackets, give them names, use the assign name in the context panel, the position vector to the generic point x, y, z. The direction vector is obtained by subtracting. So you get a vector from P to Q. That's the direction vector. And then it's P plus T times that vector. And here is the combined vector form, which is really a parametric form. X equals this, y equals that, z equals that. Now things get a little bit more interesting. We have 2 lines. One line has parameter t, and one line has parameter s. And point, direction vector, point, direction vector can be inferred or picked out of the equations, these parametric equations, which are below. We want to show that these lines are skew lines, that they don't intersect, and they are not parallel. We'll also show that for skew lines, there is a common normal between them, and hence the two skew lines lie in a pair of parallel planes, which means that you can find a distance between the two parallel planes, which is the distance between the two lines. So let's begin with a syntax-free solution. And there'll be some entry of data here. Begin by loading the Student Multivariate Calculus package. Then we have to define the two line objects. This is parametric equations for the first line. This is parametric equations for the second line. So you need a list of parametric equations. List of parametric equations. Make line and give it a name. So let's illustrate some of this stuff here. I'll just make it live for you so that we can bring up the context panel in a few places and see what some of this stuff looks like. So you make this list, Student Multivariate Calculus, lines and planes, and you have the option line. And since it sees, Maple sees t in each equation, the parameter is t. Down here, when you do that, lines and planes, if I can hold my hand steady, see Maple says the parameter is s. Assigned to a name, use this option in the context panel, and I have used the names L1 and L2. So then I want to verify skewness. So I write the names L1 and L2. And here I'll again activate those two. If you put your cursor right here on the two names, Maple doesn't know what those two names stand for. See, it doesn't realize that you're looking at lines and you want to ask it, make a query. That's why you have to do a evaluate and display in line, which you can get from here. Evaluate and display in line. I guess you click here, you get evaluate and display in line, which you can do from the keyboard. I always use Control equal. That's what my fingers are trained to do. I think Alt Enter I think is equivalent to that. If Maple knows what the objects are, and you go to Student Multivariate Calculus, lines and planes, now it says, okay, I recognize these are two lines, and you want to ask me a question about these two lines, and you see the things that you can obtain or query about. Angle between, here you have the option, you say, well, are these skew? And Maple says, yes, true, they're skew. And if you had select, are they parallel? Maple would have said no. Do they intersect? Maple would say no. To find the common normal, you take the two lines, and since you get the option to make a plane, the plane would contain the first line and be parallel to the second line. There is a common normal between those two planes, and so you then query, let's make this active, you then query that plane that has been created, and you can ask for the normal. That's the common normal. Alternatively, you could take the first line, query for its direction vector, give it a name, I gave it v1. Same thing for the second line, direction vector is v2. then you take the cross product, and the cross product of those two directions would be the common normal. Now, where did I get that cross product symbol from? Well, I've hidden my stack of palettes over here. I get that cross product symbol from my favorites palette. Where did I find that? Well, in common symbols, you go down here and you see, oh, there is a cross product symbol. If you right click on that, you have the option to add that to your favorites palette, which is what I did with all of these items in my favorites palette. And since I'm not doing any typing for you live, I've got that stack of palettes closed. To find the distance between the two lines, what we've done here is, here are the names of the lines. You do a evaluate and display line or control equal. So now you actually are looking at the plane objects. Here, let's activate this line, and you can see when I go here in Student Multivariate Calculus, lines and planes, you can ask for the distance. And here Maple gives you the distance exactly. And here I have floated it by the approximate option. I picked 10 digits. Now, what would it be like to do this with commands? Well, you'd have to bring in the Student Multivariate Calculus package, use with. You would define the line object with the line command. You would apply it to that same list, and you would give it a name, and there's your assignment operator, colon equal. So here are the two lines. RSkew is the command for the query. Are these two lines skew? You get back true. RParallel is the query for parallelism, and intersects is the query for do these two things intersect. You could form the plane that contains the line L1 and is parallel to the line L2 by applying the plane command. And then I have wrapped around that the getNormal command. So the plane object has been formed, but I don't see it because I simply want to apply the getNormal command. That's one of the advantages of the commands, is that you can wrap one around the other. It is a little bit more efficient, but you have to counterbalance that by the need to constantly either memorize syntax or look syntax up every time you need it. Alternatively, you could apply the getDirection command to each line and take the cross product of the vector that results from the getDirection command. Distance command applied to the two lines would give you the 16 over root 11, and here I just floated it to 5 points. And the one thing that's not in the context menu is the getPlot command I pointed earlier. And also the thing to point out here is the getPlot command operates on one object at a time. You can't give a list of objects so that you issue one getPlot command and it applies to a bunch of objects. You have to create the individual graphs and then join them with the plots display command. So here I'm graphing the first line, here I'm graphing the second line, here I'm graphing the first plane, here I'm graphing the second plane, and so when you put it all together, you get a picture of two planes, and they appear to be parallel. You get one line lying in one plane, and the other line lying in the other plane. That's the fixed point, that's the red dot. The green arrow is the direction vector. So you can construct the figure via the use of this getPlot command. The traditional vector solution. Okay, I would begin the traditional vector solution, my classes, with this picture. It's really useful to have in the student's mind the picture of what we're trying to do. These are the two lines, one in black, one in red. They lie in a pair of parallel planes. The green line represents the direction of the common normal. The way you would work this with a pencil and paper is you form two equations and two unknowns. X of t equals x of s, y of t equals y of s, and you solve for the values of s and t that makes that true. So here is the image. You're on the ground looking up in the sky, and these two lines are condensation trails from two airliners. And you look up and you see those two lines in the sky. You stand on the ground looking up, and you would like to know the coordinates of the point on the ground where these two lines seem to cross. That's what these two numbers will tell you. So you take the z-coordinate on each line, this line and that line. You plug in the appropriate number for s or for t, and it tells you the height above the ground that z-coordinate lies. If these two z-coordinates are different, then one line lies above the other. If those two numbers were the same, then the two lines would cross. That's how you work that with pencil and paper. To show that they're not parallel, you would take the direction vectors for each of the two lines. Here I've called one P and one Q, and their cross product is both the common normal and it's non-zero. If it's non-zero, then P and Q, these two direction vectors, are not collinear. If this were the zero vector, P and Q would be collinear and the lines would be parallel. But since this is not the zero vector, they're not parallel. For part B, we've already done that. The cross product is not the zero vector. It is the common normal. We have found that. And for part C, let's use this figure to set our thoughts in order. Black line, line L1. Red line, line L2. The green line is along the common normal. You have a point on the first line. Pick a point on the second line. You can get a vector from point A to point B by subtraction, B minus A. Project this vector, this blue vector, onto the common normal. The length of that projection will be the distance between the planes. That's the concept that we will embody in these calculations. The vector A, the vector B represent these 2 points. They're position vectors. Subtraction gives you the vector V, that's the blue vector. Projection onto n, v dot n, over the length of n, and it gives you 16 over root 11, which we saw twice before to be the distance between the parallel planes, which you take to be the distance between the lines. And one last thought. Actually, you could do this through the calculus by minimizing the distance between the two lines. But that distance is a function of two variables. And at this point in the course, in this first unit, the student has not seen partial derivatives yet. And so I have not included that here because typically the student would not have been exposed to the notion of a partial derivative, and that's what you would have to take to do a minimization. For our fourth example here, distance from a point to a line. Distance from a point to a line. Syntax-free solution. So we load the package, Student Multivariate Calculus. Here is the point. Which is the fixed point on the line. Then you have the vector, which is the direction of the line. You make the line, and you give it the name L. We've done this 3 times already so far. Then you have the name of the line, L, and the point P, whose distance to the line you want to measure. Bring up the context panel, you will have the option to get the distance. So if we, what has happened? The help page for that came out. I simply want to reactivate that, reactivate this, so that I can show you here where that distance option would be. Student Multivariate Calculus, lines and planes. Maple sees what we're working on, and you have the option to get the distance, and it was that that distance selection that gave us this number, and then I used approximate to float it. To do that through the set of commands, you would load the student package using with. You would form the line object, point and direction, assign it to the name L. You apply the distance command. Line, the point from which you want to measure the distance. I've given that the name D so that I could apply the eval F command, which is the floating point evaluation. Apply it to the name D, and we get back the value 4.65, etc. Again, you can notice that you have to know Maple commands. So users who know Maple commands will find this to be convenient and comfortable, but a class of students who are seeing Maple for the first or second time, who haven't got a head full of Maple commands, I think it's far easier to use the point and click approach. Now, the typical textbook uses a projection approach to this calculation. Now, begin with a figure. Now, the given line, which is in black, and the point P, which I believe was at some point brown, determine a plane. You have a line and a point, not on the line, you get a plane. So that's what we have drawn here. We've drawn this plane. This green dot is a fixed point on the line, and the red arrow is the direction vector for that line. Point P, that dot, this green dot, determines a vector. So this vector is in black, and I've given it the name T. If you project that black vector down onto the line and get the orthogonal component, which is what this green segment represents, well, then the length of this green segment is the distance from this brown dot to the line, from P to the line. So that's the concept behind this projection approach. Now we have a task template that will do that projection in a point and click fashion. So what are the task templates? So you go to Tools, Tasks, Browse, and you have a table of contents of 347 task templates. The one we want is in linear algebra visualizations. It is this one, projection onto a 1D subspace. So the test template is this thing down here. You insert it by clicking one of these two buttons. Default content means you get this extra verbiage. Minimal content means you get enough to make the thing work. I've already got it embedded. In order to make it work, we have to define a few things. So the items that you define are the point A, but you define it as a position vector, the direction vector V, that's along the line, and the point P you define as a position vector, and you write that out and you use the context panel to assign name. Then I've got the test template embedded. What am I projecting? The vector t, which is essentially p minus a, so I just put in p minus a. And I'm projecting it onto the vector v. Remember, the vector v was in red, so I put a little red here. The projection down onto the vector v is drawn in this diagram, which I obtained by clicking that graph button. It's projecting down here this red component, so I put some red here. I'm interested in the orthogonal component. That's in green, so I put some green around it. The length of this vector is the distance that we're looking for. Now this calculation is normally done from first principles in your typical calculus text. You want to project this vector t, which is p minus a, that was the black vector. So you define it, then project orthogonal component you get by subtraction. So it's t minus t dot v over v dot v, v. And that's this vector. And if you want to compare, this vector and this vector are the same, and we want to get the length of this vector. So if we would go to the context panel, you would see here norm, and you would pick Euclidean norm. This is the Euclidean norm exactly, and this is the Euclidean norm as a float, and I believe we've seen that number earlier. Now, for this problem, there is an analytic solution that uses the tools of the calculus as a minimization idea. The line can be represented as a plus tv. A is the point on the line, v is this direction vector, t is the parameter along the line. P minus, this is all vectors, so that's this vector. Its norm is this quantity right here. You've seen how I got a norm previously. If you simplify this, you realize it's a function of one variable. Now, students at this point know how to minimize a function of one variable. I've given it the name f. So here's f. You can differentiate using the context panel here, differentiate with respect to x, with respect to t. This is the derivative. If you use the context panel, you can find a solve in here. Solve. Take the simplest solve. You get this solution for the value of t, which gives you the point on the line closest to the point P. I believe you would find a substitute into here. You would substitute into the quantity f, which is this length. And at 5 digits, you would get this 4.65, which we've seen before. So in this case, you can use the tools of calculus of a single variable to minimize and get a distance. For a fifth problem, we'll find the equation of a plane containing 3 given points called A, B, and C. So here is the syntax-free solution. Load the Student Multivariate Calculus package. Make a sequence of the 3 points. Bring up the on the context panel, Student Multivariate Calculus, make a plane. This is the plane object that results. Bring up the plane, get its representation. There's only one way to represent a plane. That's by this equation. So if you would like to see that happen very quickly, we can reactivate this stuff, and you would see that if I click here, I would have Student Multivariate Calculus, lines and planes. I make a plane. If I click here, then Student Multivariate Calculus, lines and planes, I can get representation. And if I pick the only possible representation, it's going to be this equation. Now the command version is given here. You load the package with, form the plane. I've used the plane command, and I've wrapped get representation around that, and the equation of the plane results. The calculus book would have a vector solution. So here's a diagram to support what we're going to do in the vector solution. There's the plane. The pinkish color thing is the plane we're going to find. These 3 blue vectors stem from the origin, and they are position vectors to the points A, B, C. Then by subtraction, pairwise, we form the green and red vectors. Their cross product gives us the normal. I've drawn it brown or gold. You have a normal and at least 1 point. You can get the equation of the plane. So to do that, you've got some data to enter, 3 fixed points, A, B, C, and the position vector to the generic point x, y, z, and these are all entered as vectors because the points are entered as position vectors. Then you need to do subtractions pairwise, b minus a and c minus a, and I've called those ab and ac. You take the cross product of these 2 vectors, ab and ac. That's the red and green vector up here in this picture. So n becomes that gold vector, and then the equation of plane vectorially is r minus a, which is a vector that necessarily has to lie in the plane, dotted with n equals 0, because you're saying this vector in the plane must be orthogonal to the normal to the plane. And there's the equation that you get back. Now there is an algebraic solution for this problem, and it will let me show you something which I think is useful in its own right. Going to define a scalar valued function of a vector argument. And I struggled with this construction in Maple until finally one of the developers showed me that this is the way you could do it. So for the argument to this function f, I want to be able to just put in a vector, not a sequence of names, just a vector. And the way to do that is to use these names v1, v2, v3, which are actually table elements, and v is the name of a table. That's really what we've done here. These would be the x, y, and z, and so that if this were set equal to 0, you would be looking at the equation of the generic equation of a plane. And so I write that, and assign that as a function. So that's up here in the context panel, assign function. So this function has to give 0 when applied to the points A, B, and C, because we want points A, B, and C, which we defined up here as vectors. We want them to be in the plane. So you get these three equations, which you can solve by simply selecting solve here in the context panel. Pick these. You don't want any all solve. You want the solve here. Solve for variables. Okay, so you want to tell Maple which variables to solve for, because you have 4 unknowns, A, B, C, D. And you only have 3 equations. But really, you have 3 unknowns, because one of those letters, A, B, C, or D, has to be non-zero, and you can divide through by that non-zero one, and so you really have 3 things to find. But we'll find A, B, and C in terms of D. So here you have A, B, and C in terms of D. Then you do a substitute into, right? Substitute into, and you substitute into f of r. And you can set it equal to 0. F of r equals 0. And this is what will be returned every quantity here. Every term has a factor of d in it. Now you can divide out d. I think the simplest thing to do here is to give d a value. If you pick negative 86, and here the way you would do that is go to evaluate at a point, use the value negative 86, and you're going to get the equation of the plane.